The MRT Lembah Klang project is an ambitious initiative transforming the urban landscape. As the largest mass rapid transit system under development in Malaysia, the project's success relies heavily on meticulous planning and cutting-edge technology. One of the most notable innovations is the Variable Density Tunnel Boring Machine, TBM, developed to handle challenging ground conditions unique to this region. This machine, specifically designed for the MRT project, offers a sophisticated solution for tunneling through complex geological formations, such as sandstone and limestone. It not only improves safety, but also minimizes potential property damage, making it a revolutionary tool for the construction industry. Construction efforts are equally challenging, with specialized machinery being used in densely populated areas. This includes phased construction techniques to divert traffic safely while keeping the project on track. The use of steel fiber reinforced concrete, a hybrid system combining rebar with steel fibers, further ensures durability in these high-demand environments. Behind these innovations, a dedicated team works tirelessly, ensuring every step of the project adheres to the stringent standards, safeguarding the future of urban mobility. The Nairobi Expressway construction progresses with 24/7 operations, focusing on earthworks, culverts, and bridge works. The project, at 45% completion, involves launching 274 box girders and preparing subgrade areas for the roadbed. Watch the Nairobi Expressway video showcasing subgrade, culvert, bridge works, and 274 box girders launched. The Nairobi Expressway project starts with clearing the path, followed by the installation of essential culverts and bridges. The Al Fayruz fish farming project is the largest fish farming development in Egypt, producing about 75% of the country's total fish output. It covers 15,000 acres for fish farming, along with 10,000 acres dedicated to free fishing lakes. Beneath many highway structures, like signs and light poles, lie deep foundations known as drilled shafts. This process begins by drilling into the ground to the required depth, often 30 feet or more, depending on the structure's load and soil conditions. A slurry mixture stabilizes the shaft walls during drilling. A reinforced steel cage is then inserted and concrete is poured to form the foundation. This method reduces vibration compared to pile driving and is commonly used by FDOT for overhead signage, mast arms, and bridge supports across Florida's diverse terrain. The video takes you through the construction process of the new Ebimik Construction Waste Processing Center in Oberglatt. Completed in just 18 months, the project involves several stages, beginning with site preparation, where excavation and groundwork were carried out to ensure a solid foundation. Advanced machinery and equipment were used throughout the construction, from handling the raw materials to assembling the processing systems. The building design focuses on efficiency, safety, and sustainability, ensuring a minimal environmental footprint while handling large volumes of construction waste. The facility's strategic layout allows for streamlined operations, maximizing space for waste sorting and processing. Once the main structure was in place, the finishing touches included the installation of state-of-the-art machinery and safety systems, ensuring optimal performance. This facility is a key player in managing construction waste sustainably, contributing to cleaner and more efficient industry practices. The construction of the facility was completed with a strong focus on safety, with rigorous protocols in place to protect workers and ensure the integrity of the building process. Specialized waste management systems were also integrated to maximize recycling and minimize landfill use. Construction of Lekki Deep Sea Port began with global equipment deployment, intensive workforce training, precise land reclamation, breakwater assembly, quay wall installation, and final integration of container handling cranes. At the West Pier site, caisson construction begins with precise excavation and underwater drilling. Massive steel and concrete structures are carefully positioned to create durable foundations. These caissons support heavy loads, ensuring long-term stability in challenging marine environments. The installation of the quay wall at the multimodal terminal project in Safaga Port involves precise marine construction techniques. A pile-driving vessel, equipped with cranes, positions steel or concrete piles along the designated quay line, as seen in the image. Workers on the vessel drive piles into the seabed to create a stable foundation, ensuring alignment with the concrete platform. The platform, already partially constructed, will connect to the quay wall, forming a robust structure for cargo handling. This setup at Safaga Port supports the port's expansion, enhancing its capacity for multimodal transport and regional trade efficiency. The Port of Aberdeen's South Harbour project exemplifies exceptional engineering. Over 5 years, key milestones include dredging, creating 9,000 acrods for breakwaters, and constructing the 620-meter crown wall. These efforts ensure the harbor can accommodate larger vessels, including those supporting the energy transition. The high-speed rail project is an integrated system of high-speed electric railways that connects the entire country with a total length of 1,750 kilometers and speeds of up to 250 kilometers per hour. It aims to transport passengers, tourists, and goods along Egypt's eastern and northern coasts, as well as to Luxor and Aswan. The project also aims to connect Egypt with neighboring countries. Siemens, alongside Egyptian construction companies, is executing the project, with EDEX handling the station, bridge, Cairo Fayum Junction, and the track for the October Garden Station. A total of 32 escalators, including 4 massive ones weighing over 30 tons, were lifted into place to equip the future iconic station, Grand Paris Express. To meet this technical challenge, a 750-ton crane was deployed. The installation at Gare Villejuif, Gustave Roussy, serving Ligne 15 Sud and Ligne 14, involved 9 floors, a 30-meter diameter, and 50-meter depth. The video highlights the manufacturing processes involved in EDEX Dahlia's landmark projects. It provides a detailed look at how the company applies advanced engineering techniques to execute large-scale, complex infrastructure projects. With careful planning and high-tech equipment, they ensure precision and quality at every step, from design to construction. When aging pipelines crack or fail, replacing them can be a major challenge, especially beneath roads or buildings. That's where pipe bursting offers an efficient, trenchless solution, restoring underground systems without the need for extensive excavation. The process starts with preparing the site. Crews excavate 2 pits, a launching pit where the new pipe will be pulled in, and a receiving pit at the other end. Once the pits are ready, the Roddy Inc. R8 pipe bursting machine is carefully positioned in the receiving pit. The next phase is inserting a steel cable or rod through the old pipeline, threading it from the receiving pit to the launching pit. This guide will pull the bursting head through the damaged pipe. The bursting head, a specially designed tool, is then attached to the front of the new pipe into the pulling cable. When ready, the R8 machine powers up. Using hydraulic force, it steadily draws the bursting head back toward the receiving pit. As it moves, the conical head fractures the old pipe outward into the surrounding soil, creating space for the new pipe behind it. The new pipe follows directly, replacing the damaged section in one continuous motion. Throughout the process, operators closely monitor alignment, speed, and tension to prevent disruptions and ensure the system works safely and efficiently. If adjustments are needed, they can pause and recalibrate operations before resuming. Pipe bursting is particularly valuable because it minimizes surface disruption. Instead of digging long trenches, only 2 pits are needed, drastically reducing restoration costs and project time. It's suitable for various pipe materials like clay, cast iron, PVC, or HDPE. Once the new pipe is fully installed, crews remove the bursting equipment, perform pressure tests, and connect the new pipeline to the existing system. Final backfilling and site restoration complete the project, often within a fraction of the time traditional methods require. With advanced tools like the R8 pipe bursting machine, aging infrastructure can be renewed efficiently, safely, and with minimal environmental impact. The arch-lock construction method is used to build efficient stormwater infiltration vaults. In Vancouver, BC, this innovative approach ensures durable, high-performance structures by utilizing interlocking blocks. The system streamlines the installation process, providing a sustainable solution to manage stormwater infiltration efficiently. This method reduces costs and time while improving the overall performance of the vaults. Ven Rental strengthens Ecuador's infrastructure with specialized tunneling, pipeline installation, and slope stabilization. Using shotcrete, anchor drilling, and heavy machinery, they deliver civil works that meet demanding quality standards. The 6-meter dome building preview showcases a highly efficient construction process. The structure is assembled using prefabricated dome panels, which fit seamlessly together. Each panel is designed for quick installation, ensuring minimal labor and time. The process emphasizes sustainability, utilizing eco-friendly materials that reduce the environmental impact. This innovative approach to dome building offers a cost-effective solution, enhancing both durability and performance. Additionally, the design allows for flexible customization, making it adaptable to various construction needs. The Lamu port construction is a key part of the Lapset Corridor project. The construction includes dredging for deepening the port, building terminals, and developing related infrastructure like roads and pipelines. The project focuses on technology transfer, skills development, and local community involvement, aiming to transform Lamu into a global investment hub and key transportation link for Kenya, South Sudan, and Ethiopia. Kenya launched the Loy Changamatak Lodwar Nadapal Highway upgrade, building earthworks, bridges, and pavements to strengthen East Africa's critical trade corridor. The video showcases road construction using heavy machinery to clear the site. Excavators move soil, level surfaces, and prepare foundations for connecting Mombasa to neighboring regions. Building walls without traditional forms is now possible with Spacecrete. The process begins with ready-mix concrete delivered from a batch plant. Thickeners and accelerators are injected and mixed directly into the pumping line, transforming the concrete into a zero-slump, highly workable material. Workers pump it into shape without needing conventional molds. Steel reinforcements are added as needed, and foam panels help define wall geometry when necessary. Even with standard equipment like a 1970s Mako grout pump, the system manages dense mixes efficiently. This method reduces costs, speeds up construction, and minimizes waste, offering a promising alternative for rapid 3D printed structures and conventional walls alike. In this video, the process of digging a pool begins with careful excavation to shape the desired dimensions. Heavy machinery, such as backhoes and excavators, are used to remove soil and prepare the ground. The crew ensures precise measurements to maintain the pool's design integrity. After the excavation is complete, the site is cleaned and leveled, setting the foundation for the next stage of construction. This process is key to ensuring the pool's stability and durability. The excavation phase is crucial as it establishes the pool's shape and depth for proper water flow and support. The video presents the shotcrete pool construction process, where concrete is applied using a high-pressure hose to create the structure. The shotcrete technique ensures a durable and smooth finish, forming the pool's shell. First, the pool area is excavated and shaped to the desired design. Then, a mesh framework is installed, followed by the shotcrete being sprayed evenly across the surface. This method is efficient, offering flexibility in design and providing excellent water resistance. The result is a strong and reliable pool structure built to last. In extreme environments like the Arctic, durable, efficient housing is critical. The Protosphere Dome offers an innovative solution. Construction starts by applying shotcrete to the form, using a calibrated mixture for consistent strength. Workers trowel the concrete surface to smooth it out, ensuring uniform thickness. Rebound material, or excess concrete that bounces off during spraying, is carefully removed to maintain structural integrity. Next, a layer of urethane insulation is sprayed onto the exterior perimeter, enhancing thermal performance. Inside the dome, the walls are painted to protect the surface and improve aesthetics. This method creates a strong, insulated structure suited for harsh climates, offering a practical alternative to traditional building methods in remote regions. The installation process for aluminum formwork is an intricate yet essential part of the building process. It begins with the careful setup of wall panels and the installation of wall ties, followed by PVC sleeves for smooth fitting. Reinforcement bars are placed, ensuring structural integrity, and sockets and switch boxes are installed precisely. The soffit and beam panels are fitted next, followed by the floor corners and slab panels, ensuring each section aligns perfectly. Staircases are installed, with beams securely supporting the formwork. Ceiling light boxes and kicker plate fixing screws follow suit, ensuring proper electrical installation. The process continues with reinforcement bars, installation hooks, and sinking plates, each step working towards the completion of a solid and durable foundation. Once everything is in place, the floor is cleaned before pouring concrete into the formwork. After the concrete sets, the wall panels are dismantled. Following the concrete pour, the structure is closely monitored to ensure it has fully cured and set. As the building progresses, attention is given to fine-tuning the placement of all panels, ensuring no gaps or misalignments. The careful sequencing of each phase ensures that the structure remains stable and secure, with no need for additional adjustments. This method minimizes waste, saving both time and resources. In addition, the system used for formwork installation offers flexibility, accommodating different building sizes and designs. The use of prefabricated elements ensures that each part fits seamlessly with the next, increasing the efficiency of the overall construction. This seamless process ensures high-quality construction that is efficient and reliable, reducing the need for additional materials and labor. The precise placement of formwork allows for quicker construction times and ensures a higher level of accuracy. The design of each panel is standardized, making the assembly process quicker while maintaining the structural integrity of the building. With the use of this system, builders can achieve a durable and energy-efficient structure. Constructing concrete walls without traditional forming moves a step forward with Spacecrete 2.0. In this experiment, standard ready-mix concrete from a batch plant is modified on-site. About 10 to 15 feet before reaching the nozzle, thickeners and accelerators are injected into the pumping line, creating a mix that stacks vertically without the need for formwork. Workers use a guided screed to shape the material, vibrating when necessary to consolidate the 4-inch thick walls. The design thermally isolates all concrete from the earth and exterior, ensuring that the thermal mass remains within the conditioned interior space, improving energy performance. This approach significantly reduces costs for constructing net-zero energy homes while eliminating the use of wood or decay-prone materials in exterior walls. The system allows continuous pumping and stacking, following the movement speed of the concrete pump. Foam panels serve as temporary supports when needed, helping maintain geometry without traditional molds. Despite exposure to the elements during the curing process, the walls have shown no shrinkage cracks after several months, thanks to careful material formulation. The earlier Spacecrete trials used mixes better suited for numerically controlled 3D printing, offering faster pumping but with minor shrinkage. This updated method prioritizes both rapid construction and long-term durability. Future development focuses on blending the strengths of both approaches, achieving effortless stacking, fast placement, and zero cracking. Even basic equipment, like an older grout pump, proves sufficient for this process, making it accessible without major investment. The experimental results indicate that stacking concrete walls directly from the pump line could become a practical alternative for affordable, fireproof, and energy-efficient housing. By refining the mix design and hardware, this technique could revolutionize the construction of sustainable homes, bringing down costs and improving resilience against environmental challenges. This innovative method also minimizes environmental impact by reducing the need for disposable materials like traditional forms and wooden supports. As the concrete builds up, the design ensures stability and prevents slumping, crucial for long-term structural integrity. The construction process is also faster, allowing for quicker project completions and reduced labor costs. By streamlining the pouring and stacking process, builders can construct high-quality walls with significantly less effort. The concrete mix has been fine-tuned to offer superior adhesion and cohesion, enhancing the durability of each layer. As a result, walls are capable of withstanding severe weather and fire hazards, making this method a great choice for safety-conscious homes. To reduce noise pollution for Zetterhaus residents, Felbermayr began enclosing the Tauern Autobahn over a 1,545-meter stretch. Work started with widening the highway and building 3 bridge structures. Over 20,000 square meters of slopes were reinforced using shotcrete and anchors, reaching depths of up to 15 meters. Tunnel construction employed open-cut methods with fiber-reinforced concrete. Each 25-meter segment was cast using coupled formwork systems. Waterproofing included concrete mats and plastic sheeting. Excavated material from tunnel boring was reused for backfilling. Despite challenging weather and soil conditions, the project stayed on schedule, enhancing traffic safety and restoring tranquility to the valley. Deep beneath the Swiss Alps, an engineering giant carved a path through the Faltenjura's delicate geology. At the Belchen Tunnel on the A2 motorway, the largest tunnel boring machine ever used in Switzerland took on the mountain. Developed by MRT Technik and Herrenknecht, the machine operated with MRT's own segment production, self-driven systems, and hot melt application techniques. Mobile formworks and intermediate ceilings stabilized excavation zones as boring progressed. Thanks to these innovations, workers could maintain efficiency even under challenging ground conditions. Prefabricated concrete segments were continuously produced and installed, allowing seamless progress. Each advance of the cutter head pushed technology and craftsmanship to new levels beneath the surface. The Scenery-based tunnel project involved the construction of a stable track bed using innovative methods. Specialized concrete and bedding materials were developed and tested on site with precision accuracy in the installation. Temporary tracks were laid for logistics, while the final track system was integrated. A dedicated tunnel cleaning train was also developed to ensure cleanliness before testing, a key step for operational readiness. The video highlights the complex process of road construction inside the Gubers Tunnel, part of the important infrastructure project in Switzerland. The work begins with the careful preparation of the site, ensuring that the ground is level and the foundation is solid. The construction team uses a combination of advanced technology and skilled workers to install the roadbed in several layers. First, the foundation is prepared with an 8-centimeter binder layer, followed by a 3-centimeter top layer, which ensures smooth and durable surface quality. A precise 3D model of the roadbed is used to guide the installation process, ensuring accuracy within millimeters. After the installation of the first layers, the area is compacted to the required density, with continuous monitoring to achieve optimal quality. The next phase involves the application of additional layers, including a base layer, with recycling material for increased sustainability. The final layer consists of high-quality asphalt that is precisely applied, ensuring a smooth and even finish. Throughout the process, various machines, such as the paver and rollers, are employed to ensure the road surface meets the highest standards. The 11-meter-wide roadbed was installed in a single pass, using the state-of-the-art paver, making it the widest roadbed installation in Switzerland. This process required expert coordination to ensure the layers were applied with utmost precision. The video demonstrates the coordinated efforts and attention to detail that go into every phase of this important project, which will significantly improve road quality and contribute to smoother traffic flow through the Gubrus Tunnel. The completion of this project marks a milestone in Swiss infrastructure development, setting new benchmarks for precision and efficiency. On a chilly April night, a massive convoy rolled out with a mission to install the groundbreaking Astra Bridge. Developed under the Swiss Federal Roads Office, this mobile construction bridge allows road work to continue while traffic flows overhead without lane closures. It represents years of research aimed at making highway construction safer and less disruptive for both workers and drivers. Installation began with over 20 low loaders transporting giant bridge components. Each load was meticulously planned to navigate narrow streets and tight highway exits. Heavy-duty bogies carried upper ramp elements, each weighing 57 tons. These sections were precisely aligned and bolted to form multi-bogie vehicles. Hydraulic tensioning systems ensured all bolts were tightened to specified standards. Simultaneously, lower ramp sections were unloaded and assembled, connecting with hydraulic and data lines. Next came the assembly of the center bridge section. In just 8 hours, teams installed 175 meters of bridge by linking intermediate segments using mobile gantries. Specialized crews operated around the clock under floodlights to maintain the aggressive installation schedule. Each unit was connected through pin joints with power and data cables secured within tight 30-minute windows. The gantries themselves are highly engineered. They stand on solid base plates during operation and fold compactly for transport. Smart sensors embedded in the gantry frames monitor stress and temperature variations in real time. Hydraulic systems lift them onto bogies, while pivot-mounted pins and wedges ensure flexibility under temperature shifts. After the structure was completed, road restoration work commenced beneath the bridge. Workers milled the old surface, applied new chippings, and laid down fresh asphalt, all while traffic safely passed overhead. Protective barriers and specialized lighting ensured both worker safety and clear traffic visibility during the nighttime operations. Standard construction equipment operated efficiently under the elevated roadway. Thanks to this modular, mobile design, the bridge could be moved to the next worksite with GPS-controlled bogies, repositioned within centimeters. The entire relocation process can be completed in a few hours, allowing projects to progress rapidly along the motorway. By minimizing disruption and boosting safety, the Astra Bridge marks a major innovation in road construction. The project shown in the video involves the demolition of train tracks along Remmerstrasse in Zurich. The process begins with the use of heavy machinery, including the Hitachi ZX670-3, Komatsu PC210-10, Liebherr A918, A918 Compact, and Takuchi TB295W2. These machines work together to remove old rails and prepare the site for future infrastructure projects. The project requires precise coordination, with each machine performing specific tasks to ensure the smooth removal of the tracks in the clearing of the site. The use of specialized equipment ensures efficiency, allowing the workers to handle even the toughest tasks with ease. The area is carefully managed to minimize disruptions to surrounding traffic and infrastructure. After the removal of the tracks, the site is cleaned and prepared for the next stage of the project, which will involve the installation of new infrastructure to improve the area. The machinery is also designed for versatility, adapting to various environmental and logistical challenges. The project progresses steadily, demonstrating the successful execution of complex demolition tasks. The demolition project along Remmerstrasse in Zurich continues with the careful removal of old train tracks. The process relies on a fleet of specialized machinery, including the Hitachi ZX670, Komatsu PC210, Liebherr A918, Liebherr A918 Compact, and Takeuchi TB295. Each machine plays a key role in clearing the site, from removing the rails to dismantling support structures. The coordinated effort ensures swift progress, maintaining a focus on precision and safety. The machines are specifically designed to handle the rigorous demands of track demolition. The Liebherr A918 Compact, with its exceptional mobility, allows for efficient maneuvering in tight spaces. The Komatsu PC210 and Takeuchi TB295 work together to remove debris and prep the area for the next phase. Throughout the process, the surrounding area is kept free from excessive disruption, ensuring minimal impact on local traffic and infrastructure. Once the tracks are removed, the site is meticulously cleaned, preparing it for the installation of new infrastructure. This demolition process is an essential step in the ongoing modernization of the area, enabling future development while maintaining the highest standards of safety and efficiency. Special attention is given to the precise handling of materials, ensuring all components are disposed of properly. The project continues to demonstrate efficiency and effectiveness, setting the stage for the next phase of urban development. Watch the transport of the Hitachi ZX670 from the Remmerstrasse track demolition site. The MAN TGX41 is used for this heavy-duty task, demonstrating the careful coordination needed to move large machinery. The precision and expertise involved ensure the safe relocation of the equipment, ready for the next phase of the project. Traditional manhole repairs are slow, labor-intensive, and risky. To solve this, the Mr. Manhole system introduces a faster, safer approach. The process begins with setting up the manhole cutter around the existing manhole. Using a skid steer, operators lower the cutter and engage the rotating cutting blades. These blades quickly cut a perfect circular section of the road surface around the manhole frame. Once the cut is complete, the removed road section and old manhole frame are lifted out together in one piece. Crews then adjust the manhole height by adding or removing rings as needed. Next, the manhole is reinstalled, leveled precisely, and secured. High-strength concrete is poured around the new installation to form a durable, smooth surface. By simplifying steps and reducing heavy manual labor, this system improves safety and efficiency while delivering longer-lasting repairs with minimal disruption to traffic. The MRT SSP line's construction involves multiple critical processes. Segmental box girder (SPG) units are cast from reinforced concrete and precisely numbered for accurate placement. With 14,000 SPGs required, precision is key. Tunnels are excavated using tunnel boring machines, TBMs, through challenging rock formations. BIM technology streamlines planning, reducing conflicts and saving costs. Real-time data ensures smooth project progression. Watch the demolition process of the former tank storage facility in Tusriederen, located on the Rhine. This large-scale project involves the safe and efficient removal of a storage unit with a total capacity of 40 million liters. The process begins with the careful decommissioning of tanks, followed by systematic dismantling of equipment and infrastructure. Heavy machinery is used to ensure precise and controlled demolition, prioritizing safety and minimizing environmental impact. The site is thoroughly cleaned and cleared, preparing the area for future development. The project exemplifies careful planning, expertise, and a commitment to responsible environmental practices. The video showcases the process of creating the Ahrensfeld-Wittefeld wind farm in Bramsche, focusing on the innovative construction of wind turbines. The project begins with the site preparation, where the land is cleared and foundations are established. Specialized equipment is used to dig and level the ground, ensuring the stability and alignment of the turbines. Once the site is ready, the turbine components are transported and assembled on site. This includes the main tower, nacelle, and blades, which are carefully fitted together. Skilled technicians use advanced machinery and techniques to ensure that each turbine is properly assembled and securely installed. The process requires precise coordination between the different teams to ensure efficiency and safety. Following the assembly, the turbines undergo rigorous testing to verify their functionality. This includes checking for proper alignment, electrical systems, and safety features. Once the testing is complete, the turbines are connected to the grid and begin generating power. The integration of these turbines into the existing energy infrastructure involves a complex process of connecting each one to the electrical grid, ensuring a seamless transition from construction to energy production. After the turbines are operational, maintenance teams monitor their performance to ensure optimal efficiency and longevity. With monitoring systems in place, any potential issues are quickly addressed, guaranteeing a steady power supply. Throughout the entire process, attention is given to minimizing environmental impact and ensuring sustainability. The final wind farm represents a significant contribution to renewable energy in the region, providing clean power and supporting the local economy. With the project now operational, it not only powers homes and businesses, but also serves as a symbol of innovation in the renewable energy sector. From start to finish, the Ahrensfeld-Wittefeld wind farm reflects a commitment to quality, efficiency, and sustainability. The successful completion of the project demonstrates the importance of clean energy solutions in today's world, helping to meet future energy demands while protecting the environment. Stena Drilling envisioned a new era of ultra-deepwater exploration. Built at Samsung Heavy Industries, DrillMax vessels combine hydraulic drilling, dynamic positioning, and Arctic readiness. The SBK line tunnel breakthroughs represent a significant achievement in the MRT Malaysia project. Tunnel boring machines, TBMs, are used to carve through tough geological layers, such as limestone and clay, forming the underground path for the MRT line. Each breakthrough is a milestone in the project's progress. These tunnels are crucial for providing elevated and underground connectivity across the city. With precise engineering and continuous monitoring, the TBMs work tirelessly, minimizing disruption to the environment. The use of advanced technology ensures both speed and safety during the excavation process. As the project advances, these tunnels will ensure smoother travel for commuters while enhancing the city's infrastructure. The breakthroughs mark a major step toward completing the SBK line. Tunneling deep beneath Kuala Lumpur, Gamuda engineers drive 9.5 kilometers of MRT tunnels, using variable density TBMs to conquer complex underground geology. Beneath the bustling streets of Klang Valley, a major engineering effort reshaped the future of transportation. The Klang Valley Mass Rapid Transit Underground Works, led by Gamuda, focused on constructing a 9.5-kilometer tunnel linking 7 underground stations from Semantan to Maluri. Before tunneling, the team relocated utilities, performed detailed soil investigations, and constructed retaining walls based on ground conditions, using diaphragm walls in Kenny Hill formations and secant pile walls in limestone areas. Tunnel boring machines, TBMs, including the world's first variable density models, tackled diverse soil challenges, switching modes between slurry and dry muck as conditions changed. Each TBM drive required precise assembly, with careful adjustments made to avoid building foundations and existing tunnels. Continuous structural monitoring ensured minimal impact on nearby properties. Specialized TBMs allowed tunneling to proceed beneath dense urban areas without disrupting surface activities. Every breakthrough marked a key achievement in the overall project timeline. As tunneling advanced, first-stage concrete linings were completed, followed by the installation of mechanical and electrical systems. Cross passages were built between tunnels for emergency access, and connecting links like the one between Inai Shaft and Tun Razak Exchange were finalized. Stations such as Museum Nagara employed top-down construction methods, progressing from roof slab to concourse and platform levels. The underground tunnels were handed over for track installation, marking a major milestone toward a modern, integrated transport system for Kuala Lumpur. Elevated viaducts rose steadily as MRT Putrajaya line construction advanced. Stations were completed with island platform designs for better passenger flow. Cable laying energized the power system, enabling train testing. Underground, TBMs driven by AI technology navigated complex geology. Drone surveying, LiDAR scans, and augmented reality tools reshape site management, ensuring progress toward a smarter, connected future. The Suez Bridge, a prominent structure over the Suez Canal, connects the northern and southern regions of Egypt, facilitating road traffic and essential cargo transportation through the canal. The Joseph Tito Bridge, approximately 2.7 kilometers long, is a crucial part of Cairo's transport system, reducing congestion and shortening travel times between different areas. The Badrashan Bridge, located on the main route connecting Cairo and the southern regions, spans 900 meters and plays a key role in enhancing infrastructure development. The bridge over the Shubra Benha Ring Road, near the duty-free zone, connects industrial areas, optimizing cargo transportation and boosting production and trade capabilities in the region. Witness the transformation of Astir Marina in Vuligmeni, a major construction project captured in this time-lapse. Led by Takal, the development began with site preparation, including extensive excavation and underwater surveying, to ensure precise alignment for the new structures. Temporary cofferdams were installed to create dry working conditions below sea level, enabling the construction of stable foundations. Large precast concrete elements were transported and carefully positioned to form the marina's protective piers and docks. Cranes and specialized marine equipment facilitated the placement of massive structural units, maintaining strict tolerances despite challenging sea conditions. Specialized divers also assisted in precise underwater placements, ensuring structural integrity. Surveying teams monitored alignment continuously, using GPS and sonar systems for maximum accuracy. Concurrently, land-based works progressed with the construction of retaining walls, service areas, and roadways supporting the marina infrastructure. The dredging operations were executed in stages, allowing the marina basin to gradually reach its target depth without disturbing the coastal ecosystem. Prefabricated elements for utilities, such as power and water conduits, were installed simultaneously with the structural work to streamline the construction timeline. Environmental barriers were deployed around work areas to contain any potential sediment spread. The project emphasized environmental protection measures, minimizing disruption to marine life during all phases. Modern dredging techniques were employed to deepen basins for larger vessels while controlling sediment dispersion. Reinforced concrete was poured in segments, allowing curing times to be optimized and minimizing downtime between phases. Electrical and water supply networks were integrated seamlessly into the new design, supporting the marina's operational needs without impacting the aesthetics. As the main structures neared completion, attention turned to surfacing and outfitting docks with mooring systems, lighting, and safety equipment. Installation of bollards, fenders, and access ladders ensured that docking areas met international safety standards. Landscaping along the promenade blended natural elements with modern amenities, offering a harmonious balance between built and natural environments. Irrigation systems were embedded beneath the walkways to support sustainable plant growth in the marina's landscape zones. Throughout the project, a meticulous schedule and advanced construction methods ensured that milestones were consistently met. Rigorous quality control inspections were conducted at each major phase to certify material strength and assembly precision. The final result is a world-class marina, capable of accommodating a wide range of yachts and enhancing the waterfront experience in Vuligmeni.